Okay, so here we go. Let's have a look. Quiet. Hey, did anybody leave a calculator in here yesterday?
No, but I'll have a calculator.
Okay. Okay, so what do we do with this? Now, in math, when we talk about sufficient means enough. Is it good enough? Necessary means it has to be there, right? There are different words in math. So we want to know which of the following are sufficient to prove that the quadrilateral ABCD is a parallelogram. So we might have to do some more work, but that would be, I'm saying that's enough. So let's look at a couple of these here. Let's draw a picture, and this definitely involves drawing a picture.
But then you have to draw like 17 pictures.
You have to draw, well, you have to, not necessarily. You can draw the same picture, but just mark it differently. Yeah, it's a hard question. I would never in a million years give this question to my regular geometry class. But
Was this on the practice? Yeah.
Okay, what's that?
Was this on the practice? Yeah, it was.
Mhm.
No one knew how to do it.
How to do it?
They just click on it, did it.
I don't know how to do it.
Yeah, I did.
But you only get one try.
Okay, so up here, please. So this was a parallelogram, right? Or did it say quadrilateral? Parallelogram. Okay.
It's easier to
Well, you're trying to prove it's
We're
parallel.
trying to prove it's a parallel.
Okay.
It says quadratic.
Oh, right. Gotcha.
No, but it makes me cry.
I asked if I could try this. You said no.
Yeah. You told me I'm not much brighter in the bedroom.
I think I should be able to try on this question.
Okay, so let's look at the first. Don't get distracted. Let's look at the first line here. So we know. Notice that all of these options have one thing in common. Angle CAD is congruent to angle BCA. Now, remember that when we list a polygon as being ABCD, those have to be consecutive vertices, right? So we have to be going around it either clockwise or counter. Doesn't matter which way, but we have to be consistent. So then we know CAD would be, that's going to be that angle right there, isn't it? So that angle is congruent to angle BCA, to that one right there. And we know angle BAC is congruent to angle ACD. Okay, so I want to know then, how can we show, is that enough? Okay, why is that enough? What's it doing that tells us that's enough?
It shows that there's the two sets of parallel.
Yeah, exactly. Because look what, this is one of those, this is really a chapter 3 kind of a thing, right? We know that if I've got this angle, let's say the single loop congruities, right? Congruences. Those are alternate interior angles if we draw those sides as lines and the blue segment as the transversal, right? And we know that if alternate interior angles are congruent, then the lines are parallel, right? So we know those guys are parallel. And then we could do the same trick up here, couldn't we? Right? The other pair of congruent angles would go with those lines and the blue transversal. And that would show us then as their alternate interiors for the orange and blue lines, that those are parallel, and that's a parallelogram, right? Right, by definition, that's a parallelogram. We have two pairs of parallel sides. Okay? So that one worked. See what I'm getting at? So all of these, if you look at all of these, everything up here, if we kind of backtrack a little bit, which I'm able to do, which is kind of nice, so we can backtrack here back to this point.
We can't do that.
I know you can't do that. It'd be nice if you could. All of them take us to there, don't they? So in each case, we automatically know.
Can we get whiteboards?
Wouldn't that be nice? So we always know this, right? We have those pairs of parallel lines. And so then really it's just a matter of saying, okay, now that we know, that doesn't look pretty good. So now that we know these are parallel, which of those situations up there are giving us an additional piece of information that allows us to conclude it's a parallelogram? like AB, this one doesn't work, does it? Right? If we look at this guy right here, AB is congruent to CD, well, that's telling us those are congruent, and that is not enough information, right? Because there's no way for us to.
Because they could be like this.
Right, and that's a good way to look at it. You could say, okay, so is there a way I could tweak this? Like in the way I would with Geometry Sketchpad. Could I drag these things around in a way that's going to make this not a parallelogram? And yeah, I could, right? I could, for example, what if I were to, let's see, how do I want to say this?
But it never tells us that those two are.
Yeah, you're right.
It never just tells us that those two are.
Okay, I'll show you. I could drag this vertex here. This length has to stay the same, right? Everybody agree? So if that's the same, then I ought to be able to swing this thing down like this, right? And it's going to get to another point down here where it would intersect that side. Now I didn't change any of the congruence marks,
Well,
right?
wouldn't it still not, would they not be parallel?
Well, no, those two would still be parallel.
But if you stretched it, then it'd be longer and they wouldn't be congruent.
Okay, but
Yeah,
what is?
but then how would those
No, it's not.
Bro, it could be traffic.
I didn't stretch anything. All I did was I pivoted this thing. So there's the pivot, and I just twisted it down there.
We just open this on Geometry Sketchpad.
I mean, we could, right?
That would help me understand.
Okay, I can do that. That's fine. It's probably not a bad thing.
Then when you put parallel,
Can I just take this test
all
for
of these
my
are-
pure estimation?
We need to be on your sketch pad.
It'd be nice.
I don't know who that is. He's amazing.
In the morning. Are you gonna be able to do this?
He's an amazing human being.
Are your guys' Yeah. Down that straight. Jesus, you just gotta go out and drive this straight.
No, that's
Just flying.
All right, so you got to tell me how to do this then. If I'm going to do this in Geometry Sketchpad, if I want to create that shape, we had the left and right sides were parallel, and the top and bottom were congruent, right? Okay. So there's a side. I want to now define a point that is parallel to that line, right? So and I'm going to put a point over here. Hang on. So I want to put a point like right over here. And I'm going to highlight that and construct a parallel line, right? Agreed? Okay. No, this is it. So now I'm going to construct those two. I'm going to highlight those two and construct a segment, right? Construct a segment. Okay. Does that make sense?
Okay.
Okay. I want to make another one that is congruent to this one, right? Okay. It has to connect to that point too, right? So I'm going to measure this. I'm going to measure the length of that one, and I'm now going to highlight that and create and hit that point, and I'm going to construct a circle by center and radius. Okay? Every point on that circle, would you agree, is that distance away from that point, right?
Wait.
Right? That's the definition of a circle. That's what a circle does, right? So any point that I use to construct, any point between this center of the circle and the edge of the circle is going to be congruent to that segment. Has to be, right? Because they're the same length. That's all it takes to be congruent segments. Everybody see that? So I could pick this one. If I pick the intersection, right? If I pick that how do I do that? See, I think I can go like this. Let's try it. Right there. Okay, that's on the intersection, right?
intersection.
They're really easy.
Okay, so that looks an awful lot like, let me do this real quick. If I create that intersection or segment, let's make this go away. Well, that's a parallelogram, isn't it? Right? So far I haven't proved my point at all, but watch this. Oops, hang on. Thought I was pretty smart there, but it didn't work. Okay. Do it again. I gotta go back. Display. I messed something up, but it'll still work. So I could also, though. Yeah.
If you had the circle, would that work?
No, it'll still have the same. Yeah, it won't work. But I could do this. See, I could also take that one right there, that bottom side, and pivot it down. What have I done? Nothing. I mean, it's still the same length.
What about
right?
the angles?
Well, the angles have changed, meaning it's not a parallelogram. You see my point?
But then what it said earlier.
But you could put it on the other side and go off of that side.
What?
I mean, you may not see this. I can't guarantee you're going to see this. I think some people are seeing it, some people aren't. If you really focus, I think you can. But I'm not going to spend a ton more time on it. I mean, it's.
I just didn't realize that like the circle went outside of it, so I thought the
Oh,
circle
okay.
was curved in.
I was like, how did angles change?
So I didn't see how it was
Oh,
and how I.
So it might help to do if I do this also. Like if I go.
Sorry, that makes sense now. I was confused.
Okay. Are you seeing what I'm saying though?
But it said that the angles were the same.
No, it didn't. No, it didn't. All it said was this. All it said was. Said, well, look what it said. It said those angles were the same, but those angles I haven't even drawn. Those are the angles that show that this line is. Oh, I see what you're saying. But they still would be though. They still could be.
They'd still be.
They still would be. They still would be congruent because if this gets pulled down here, they will still be. They'll still be congruent. All those angles are doing is telling us that these sides are parallel. That's it, right? Because they're alternate interior angles. I'll show you. I'll show you in a second. So those are saying that the sides are parallel, and this is saying that the top and bottom are congruent, right? Okay. So that's true. That's congruent to that, which is congruent to that, right? Those are still parallel, right? But either one of those would work. There's nothing preventing me from picking either one of those. And because I can pick the bottom one and not violate any of the conditions, it's not a parallelogram, right? It's not enough for me to show that it's always a parallelogram. Right? See my point? Okay.
I wasn't confused.
I wasn't confused before this, but now I'm even more confused. Now.
I actually understand something.
Whoa, I want to go home.
Okay, and then I think maybe one thing that people were asking, I think Jill's, let me just show one other thing here real quick. What Jill was saying, I get her point, it's a good question. She's saying, what about the angles that are supposed to be congruent? Oh, sorry. That's not what I meant to do. Oh my gosh, let's see, that's there. Like that, how about, there we go. Okay, so, let me try that again. That guy, that guy. Oops. There we go. Okay, so these angles right.
They're still too parallel.
Those angles are still congruent. Okay? See what I'm saying? Everything's still true. Okay.
That's it?
Yep.
What?
Wanna go to the lab?
I'm not going to. I'll give you two. Well, you'll get two next week. A bunch next week.
The
Yeah, so the thing, yeah. The tools has that teaches really. Punch in the face for me right away.
You know, invest
I'm just gonna tip it.
All right.
in. You don't want to.
I'm just gonna do Why is geometry my question?
Okay, what about one like this?
Well, I don't want to give. It's so easy.
What do you guys do with that coal? Like you sit? It's like.
Okay, what about these?
What is that?
So on the, I just want to make sure everybody understands what's going on with this. Okay, you ready? So we want to know, identify the quadrilateral ABCD based on the description. Select the most specific name that applies, right? So if it's a, for example, if square works, does rhombus?
I don't know.
Yes.
Does Panda
No, how come?
Because square is more specific.
Square is more specific, exactly, right?
I thought.
Okay, so what does this tell us then?
a lot of money?
Okay, I'm about to do another seating chart here. This is getting a little ridiculous. There's too much talking going on. It's just too chaotic. These concepts are too big. You have to raise your hand and be polite to other people. You can't be blurting things out. It's hard. I know it is. If I'm a student out here right now, I'm kind of ticked at maybe some people that are being a little too loud. You can't do that. That's not polite. I'm going to have to ask you to move someplace else if you can't control yourself. All right. AB is parallel to CD. So we know that's true, right? What does that mean? It's not congruent. AB is not congruent to CD. So what is this not? It's not a parallelogram, in fact,
Not
is it?
squares.
Right? So if it's not a parallelogram, that would be the best thing to say, because then it's also not a bunch of other things. Anything that's also a more specific parallelogram is ruled out. So we could go up here and just do this. Right? Those are all gone. See what I'm saying? So what else do we know? Angle A is congruent to angle D. So if those angles are congruent, and this is not, it's not a parallelogram, what could this be? Yeah, the only thing it could be is a trapezoid, right? Does that make sense? Okay. Could we have consecutive angles in a kite that are congruent? No, we can't. Look at a kite, right? A kite, those angles are congruent, those ones are not, right? Quadrilateral, well, I mean, these are all quadrilaterals. Hopefully we can do better than that, right? So it's going to be a trapezoid. Does it have to be an isosceles trapezoid? No. It can be, but it doesn't have to be, right? So the answer would be trapezoid.
And we haven't been given enough information to say that it is an isosceles.
Right, we haven't been, exactly. Okay? Because we know these sides, well actually we haven't been given enough to say that it's is or is not, right? Because we know that these have to be the bases of the trapezoid because they're the parallel sides. So what could it look like more realistically? Well, if these angles are congruent, then we know one thing. I guess we could actually surmise one thing about this. What do those angles have to be? If they're congruent, yeah, they have to be supplementary too, don't they? Because we know that in a trapezoid, those angles would have to be supplementary because these are parallel sides, and so those are consecutive interiors, right?
So it could be an isosceles triangle.
And you're right. So then actually, Kirk's right. It couldn't be isosceles because if it were isosceles, what would have been true?
It would have been a parallel.
Yeah. Then it would have been a square, exactly, right? And it wasn't. Okay, or at least it would have been a rectangle, right? So it has to just be a regular trapezoid. Okay? There's a lot of thinking that goes into those. I mean, they seem like they'd be easy questions, but those are some of the hardest questions I think we've had all year, really. Okay?
Multiple choice ones.
Okay. So I think, you get the idea. You'll get more time to work on this stuff. What I want to do today, actually, I want to take a little time, and I want to introduce you to something, not because I'm trying to bog you down with, here's why I'm doing this. Let me just justify this before you think this is a bad idea. Because it's not negotiable anyway. I'm gonna get you going to where when people finish up the test next week, so I'm gonna give you some time to finish it up. When people finish up, I want them to be able to move on to something else. And so I want to be able to put up like an introductory assignment in chapter 7 so people can start to work on that. Okay, that's why we're doing this. This in no way means that you can't go on and do more testing. You can, right? You can, but that's why we're gonna, and we don't really have time to go down and test today anyway, so.
Yeah, 17 minutes.
That's not very much. So let's talk a little bit. This is a really cool chapter. This is a very important chapter. I'm excited to teach this one. It's about transformations.
Is that when you have to go pee, but someone's in the bathroom on a plane?
That's not quite what it is. Okay, so rigid motion in a plane. So this is really important stuff. This has to do with how can we take two-dimensional objects and how can we move them around any place in their plane, the plane in which they sit. Okay, this is a big deal because I'll tell you why in my mind this is so important, because this starts to introduce you to types of symmetry, exploiting types of symmetry. Okay, in math, that shows up in all kinds of, probably the first place you really see it is in geometry for obvious reasons, because it's symmetry that you can see visually pretty easily, right? But it shows up in other ways too. It shows up in algebra. We just had a review of this in my calculus class the other day. It shows up in algebra when you're talking about the shapes of functions. There are certain kinds of symmetry that we can exploit. I'll just give you but you're going to be doing this in a few years. One of the things we do in calculus is we try to sketch a graph so we can include all of the important information about that graph. So for example, we would do things like this, like if we were able using calculus to identify that we had a relative maximum at some point right there in the plane, that means a peak, a smooth peak, and we had a point of inflection right there, and it was asymptotic on the x-axis, then we might know that it looks like.
I have no idea what it is.
Okay, well, it just means that we would know that the shape of that curve was kind of like that. But if we also knew that this function had what we call even symmetry in algebra, we would know that it would have reflective symmetry across the y-axis. And so we could avoid, maybe it took a lot of work for us to figure that out. We have to repeat the work on the other side of this asymptote at x equals 0, but no, we don't.
What does that mean?
Okay, well, I mean, those words are, all that means it's a place where the function either moves down towards negative infinity or up towards positive infinity, for example. So it never gets there, but it kind of just does. Like if I were to pan out with this, so I got a long ways away, this function might look like this. But then this thing still just gets closer and closer and closer to the y-axis, never touches it, but gets always a little bit closer. See what I'm saying? And so we'd say it goes down to negative infinity, because it never gets there, it just keeps going down always.
How can it get closer but never touch it?
Well, okay, in the same way, in this way. What if I said, here's an interesting question, I can't remember if we talked about this earlier or not, but if I said I'm going to take every second from here until eternity, I'm going to take a step closer to this door, right? Halfway to the door, let's say. I'm going to always cut my distance in half. Do I ever get to the door?
No.
I don't. That's the same way. Do I ever, what would you say that the limit of my motion is? What's the only thing that I'm always getting closer to? Well, yeah, the door, right? If I had a super fine tip Sharpie and I made a dot with as incredibly mathematically fine point, is there any point that I could draw on the floor that I wouldn't eventually step on? That's a good question, huh? Is there any point I could make a mark on the floor that's not on the door that I wouldn't eventually step on? The answer is no, there's not. Every point you make, I will eventually step on, and yet I will never get to the door. You see, that's a weird concept, but that's the truth, right? That's a concept that we'll explore, that we'll, in this room, we'll explore when you're seniors. That's what we'll explore in calculus, right?
Why is that a thing?
Why is that a thing?
Yeah.
Oh, calculus is the best.
Who's like, oh, also you can't like divide by 2 over and over again.
Okay, so anyway, back to business here. So the point I was making though, and you asked me about asymptotes, there's a good explanation of kind of asymptotic behavior. But if I knew what the symmetry of this function was, if I knew it had even symmetry, I wouldn't even have to do the other half. I could just say whatever I got there, I'm going to get the same thing over there. And I'm done, right? In physics, we can do even other weirder kinds of symmetry. We can do things like time symmetry. Like we know that oftentimes the system, the laws of physics behave the same going forward in time as they do going backwards in time, which is really bizarre, but they do. Only a few of them change. So very, very few laws in physics are any different going forward in time or going backward in time. And so that's an important symmetry. We can look at a system, a physical system that's evolving either forward in time or we can roll it backwards in time a little bit to see earlier conditions mathematically. And it works because we have that kind of symmetry. Okay? So this is this kind of thinking. I just want you to know that even though we're going to be talking about geometrical symmetries, there's all other kinds of symmetries that you've never even conceived of that also will eventually apply. You know, it's all the same kind of thinking. All right. Okay, so rigid motion in a plane. Not that big a deal. I mean, it's important, but it's not like this introductory section's all that hard. There's 3 things we can do to make rigid transformations. So the shape is going to be moved from one place in the plane to end up in another place in the plane, and it's not going to have changed. It's going to have been rigid. It hasn't been bent or flexed, right? That's what we mean by rigid. It could have been reflected, it could have been rotated about some point, or it could have been translated. And what does translated mean? Right? Yeah, it means sliding. We can slide it in the plane. Okay? Those are the only 3 things we could do, or we could do some combination of those, but that's it. Anything else we do is going to change the shape of the thing or the size, so it's not going to be a rigid transformation. Some vocabulary we got to get used to. To produce new figures by doing these things, the new figure we call an image, and what we started with, the original, so to speak, is the pre-image. So we always start with pre-image and then create an image by doing this stuff, right? The operation that does that, whether it's a reflection or a rotation or a translation, or it could be a combination like a glide reflection or something, you know, which we'll talk about later, some combination of those, that's called an operation. Right, so we're doing some kind of operation to move this thing from there to there somehow. The 3 basic transformations, as we said, reflections, rotations, translations. So we're saying, oops, I think they said, was blue the original? Yeah, it was. So blue is going to be the pre-image and red is the image, right? Do you agree that this is a reflection? Right, can you see that? Can you see that if I drew the blue shape in wet ink and I folded the paper right there, I would create the red imprint? Right? Okay. I want you to see if you can notice something about these in a second. Do you see that this is a rotation? This is like saying if I put a tack in the paper and I spin the paper a little bit, well, the blue shape ends up there.
Is that a 90-degree one?
Yeah, it is. 90 degrees. And how do we tell? Because here's how you can tell. Because if I take 2 points, that point right there, would you agree, maps to that point? And that's the vocabulary we'll use. It maps to it. It starts there and it ends there. If this is the center, then this is the arc that if I were to drag that point across, wouldn't it just make an arc like that to get there? Well, what's the angle? 90 degrees. Right? See what I'm saying? Okay. And this is a translation. We just slide it. Okay, now in which case, I'm jumping ahead a little bit, but the orientation of the object describes whether I would move clockwise or counterclockwise around it to see the points in a specific order, right? Let's say that it's like an F, right? So let's say we're going to start at the bottom and we want to walk around like that, right? To start at the bottom and then walk around the top of the letter, we would call the top of the letter, we would go clockwise for the blue one here, right? How about over here? Counterclockwise. It changed it, didn't it? So it switched the orientation, right? How about here? Clockwise, 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 clockwise. So only one of those changed the orientation, and that was the reflection. Okay, the other ones didn't. Okay, that's going to be important in the future. Okay. So this is another thing you just got to be aware of. Whenever you look at representations of these transformations, we'd always start, for example, with vertices like regular letters. And then once we've done something to them, once they've undergone one of these transformations, then we put a prime, meaning they got changed. What do you suppose we would do if we took, so this is the pre-image and that's the image, right? Start with the pre-image, end up with the image. What if we took that image and we did something again with it? So it became the pre-image of another image. How do you suppose we would label A then? We'd label it as, so see what I'm saying? This A maps to A prime. A prime maps to A double prime. Yeah. Okay. Right? See what I'm saying?
So then it goes to triple prime.
Yeah, and then we go triple prime, et cetera, et cetera. Right. Okay, so what is this? What is this one? Tell me, what kind of transformation is that? It's a reflection. Yeah. It's a reflection. Everybody see that?
Yep.
Okay. Okay, how could, well, we'll get there. I won't jump the gun too much. Yeah, you're right.
I remember this from.
You remember seeing this stuff a little bit? Okay. I'm not gonna worry about that. You guys, that's no big deal. You can, for you folks, that's trivial. Okay.
I really like how
I'm not even gonna mess with that.
formulas in all caps.
Okay, this is what I wanted to get to, because we're almost done. Isometry. Okay, in isometry, this is kind of our math way of saying a rigid transformation, because I want you to think about what the roots of this word are. What's iso mean? Same. Yeah, equal or same, right? Iso, and then anytime you see meter or metry or something, that means has to do with measurement, right? So this means same measures. So all of the measures, everything about they would be congruent, right? Everything about them would be the same. Angle, or the angle sizes, the side lengths, all that stuff. So that's, isometry is a rigid transformation. And that's what we call them, isometries. Is that an isometry?
Sure.
Looks like it. What kind?
Reflection.
Okay, reflection, good. Is that an isometry?
No.
Nope, no change, right? Exactly. Is that an isometry?
Yes.
What kind?
Rotation.
Rotation.
90-degree one.
Is that an isometry?
Yeah.
Yeah. Okay, good. So how do we represent that? When are we out of here?
5 minutes.
5 minutes, okay, that's good. That's enough. So this is how we represent it. We use an arrow like this to say that we're going from triangle ABC to triangle DEF, right? So it's mapped onto, this is what we're starting with, and that's what we end up with, right? So this means it's undergoing a transformation to become that, okay? Notice that the vertices have to line up. A goes to D, B goes to E, and C goes to F, just hiding back there, right? Okay. Okay. So, what's the length of XY?
30.
Everybody see that? The length of XY has to be 3 because they're telling us that the blue pre-image is mapped onto the red image, right? And maybe it's a little difficult to see. You kind of have to, and you're getting better at this, I'm sure, and you continue to get better at just kind of moving things in your mind. But you don't even really have to do that because they tell you everything you need to know. Notice that XY matches up with PQ, right?
How do we know for sure that they're exactly the same?
Because it's telling us. right here in the diagram, PQR is mapped onto triangle XYZ. The mapping is a rotation. So if we know, if they're telling us that's true, a rotation is an isometry, right? It's a rigid transformation. So all the measurements would be preserved, be the same. So then what used to be PQ has now become XY. Well, PQ had a length of 3, so does XY. Didn't even really need to picture. Okay.
Hey, I get it.
All right, that's our brief introduction to isometries. Not a big deal. A little short introductory assignment, and then we'll get into some better stuff.